So now write down the heading as XIII Chapter, Electromagnetic Waves. Okay. So as the name suggests, electro refers to electric field, and magnetic obviously refers to magnetic field, and waves refers to disturbance. So if you're able to talk about a wave, which is a combination of both electric and magnetic fields, then that kind of a wave is called as electromagnetic wave, but it has something specific to be done. It is not like, just like that if you have electric and magnetic field and it is a wave, you cannot call it as electromagnetic wave. There are certain rules to be followed. For that, we need to look at each term in detail. So first, we will try to understand what waves are. So basically, what is a wave? I've already given you the definition. Wave is basically a disturbance, right? So wave is a disturbance which is created to transfer energy from one place to another. So it is a disturbance which is created to transfer energy from one place to another, right? So when that is the case, wave needs a medium for propagation. So it needs a medium for propagation, but there are certain waves which do not require medium of propagation also. So based on whether they need a medium for propagating or not, they are classified into two types. What are they? Mechanical and non-mechanical. So what do you mean by mechanical waves? Mechanical waves require a medium for propagation. Non-mechanical do not require a medium. Do not require a medium for propagation. Right? So just give me a minute, I'll be back. Yes. So mechanical waves require a medium for propagation. Non-mechanical waves do not require a medium for their propagation. Similarly, based on, so generally what happens with respect to a wave? Whenever you have a particle, so the particle will undergo something called as vibration. So particle undergoes vibration and energy undergoes propagation, right? So energy propagates and particles vibrate. So based on the direction in which the vibration and propagation is taking place, again waves are classified into two types. What are they? So waves are again classified as longitudinal and transverse. So what are longitudinal waves? Longitudinal name is suggesting along the length. So vibration and propagation are along the same direction. Okay, vibration and propagation are along the same direction, whereas transverse means vibration and propagation are in perpendicular direction. So if this happens, we call it as a transverse wave. Is it clear? Okay. Now, having all these points in mind, we will try to define what an electromagnetic wave means. So electromagnetic waves are basically time varying electric and magnetic fields. I repeat it again, time varying electric and magnetic fields which are mutually perpendicular to each other along with the direction of propagation. If you're having a time varying electric and magnetic fields which are mutually perpendicular to each other along with the direction of propagation, you call that kind of a wave as an electromagnetic wave. Is it point clear? Right? So how is it supposed to look like? Let me show you. So you have to see this. So what happens is the electric field and the magnetic field vibrate mutually perpendicular to each other, and if you look at the direction of propagation of both, they are perpendicular to each other. So that is why electromagnetic waves are transverse in nature. So it is because of this reason only electromagnetic waves will be able to exhibit a property called as polarization. they exhibit a property called as polarization, which will be discussing about it in wave optics. I think that part is deleted. Let's just give you a brief introduction of it. Okay, is that clear? So this is how it looks like. So if you see, this is also called as a plane progressive wave. You would have heard of this term, right? Last year in waves. You have heard of what is a plane progressive wave? Yes or no? To some extent. No. Okay. If I write the equation, you will understand it. Okay. Now we'll see what it is. So write down equation of EM wave, which is also a plane progressive wave. See, plane progressive wave, or you would have heard something called as a traveling wave. Have you heard this term at least? Traveling wave. They both mean the same. Traveling wave or plane progressive wave, they mean the same. So the equation looks like this. If you take the electric field to vibrate along y direction and for it to propagate along, let's say, z direction, okay, then you can write this as E naught into sine of kx minus omega t. Have you seen this equation? You would have seen something like this. Y is equal to a sine of kx minus omega t. From this one, you will have something called as standing waves, nodes, anti-nodes. So this is the equation. So electromagnetic waves are something similar, except the fact that here, instead of kx, I'll write it as kz, where E naught is called as the amplitude of electric field, k is called as the K is called as, any idea? It's called angular wave number. You know what is a wave number, right? Wave number is 1 by lambda. If you multiply that 1 by lambda with 2 pi, you call it as angular wave number. So k will be written as 2 pi divided by lambda. What about omega? So omega is called as angular frequency. So how do you write omega as? Omega is written as 2 pi by capital T, or this can also be written as 2 pi into f. Right? And Z represents the direction of propagation. Z represents the direction of propagation. And an important point here is negative sign indicates that the wave is propagating in positive Z direction. So negative sign indicates that the wave is propagating in the positive Z direction. Okay. Having this in mind, if electric field is along y direction, propagation is along z direction, then what would be the direction of magnetic field? So magnetic field would have been along x direction, and this would be equal to B naught into sine of kz minus the same omega t. again the same k angular wave number, angular frequency, everything else is the same, and V naught is the magnitude of the magnetic field. Okay. Now, moving on to the next concept that says that speed of light. So, speed of light, C is defined as the ratio of E naught to B naught. Okay. So, ratio of E naught to B naught is what is called as C. That is the speed of light. And secondly, you know that 1 divided by 4 pi epsilon naught is how much? 9 into 10 power 9. Mu naught divided by 4 pi is 10 power minus 7. Okay. If I divide both the expressions, that is 1 divided by 4 pi epsilon naught divided by mu naught divided by 4 pi is equal to 9 into 10 power 9 divided by 10 power minus 7. 4 pi and 4 pi are gone. Then you will have 1 divided by mu naught into epsilon naught is equal to 9 into 10 power 9 into 10 power 7. What is it going to give you? 9 to 10 power 16. It will give you meter square per second square. So this is 1 by mu naught into epsilon naught. So taking square root on both the sides, 1 divided by square root of mu naught into epsilon naught is going to be equal to 3 into 10 power 8 meter per second. What is this? This is the speed of light. So speed of light is also written as 1 divided by mu naught into epsilon naught, or you can simply write it as E naught divided by V naught also. So these are the two important mathematical expressions in this chapter. Is that clear? Okay. Next. Shall I proceed? Those who are online are able to understand?
Yes, sir.
Yes, sir.
Yes. Good. Okay. So I hope you made a note of all these points. Did you?
Yeah, got it, sir.
Yes, sir.
Okay. Next. So based on this concept, let's try out this problem. There is a plain electromagnetic wave of frequency 25 megahertz. Right? So what is the frequency given? Is it angular frequency or simply a frequency? This frequency. So F is equal to 25 megahertz. Mega is how much? Mega is million basically. Million is 10 power 6. So 25 into 10 power 6 hertz, which travels in free space along the x direction. At a particular point in space and time, electric field is given as 6.3 times J cap. What is B at that point? I gave you the relation already. C is equal to C is equal to E by B, which implies B will be equal to E divided by C. E is 6.3 divided by 3 into 10 power 8. So how much will you get? 2.1 into 10 power minus 8 Tesla. Now what are they asking? What is B as a vector at that point? So the magnitude of B is 2.1 into 10 power minus 8. What would be the direction of it? Why is it Z direction? Because the wave is propagating in X. Electric field is along Y. So B should be along Z. Okay. Next is example 8.3. Try it out. The magnetic field in a plane electromagnetic wave is given as By is equal to 2 into 10 power minus 7 sine of 0.5 into 10 power 3x plus 1.5 into 10 power 11 t Tesla. K is in 2 pi by lambda. So question, buddy, what is the wavelength and frequency? So K will 0.5 into 10 power 3. It is radian per meter. Sharia. Uh, 3.14. So K is equal to 0.5 into 10 power 3. 2 pi by lambda is equal to 0.5 into 10 power 3. Lambda will be equal to 2 pi divided by half into 10 power 3. That is 4 pi. 4 pi into 10 power 3. 10 power 3 minus 3. Because it can't be that long. So 4 pi now, how much is it? 4 into 3.14. Something around 12, 12.6. So 12.6 into 10 power minus 2 meter or 1.26 into 10 power minus 2 meter. 10 power minus 2 meter is 1 centimeter. So it is going to be 1.26 centimeter. Is that clear? And what is the value of 1 by t? Sorry, they asked the frequency, no? 1 minute, I'll change the color. 100. Omega is equal to 2 pi f, but what is the value of omega? 10 power 11 is equal to 2 pi into f. Approximately 0.25. 0.25 into 10 power 11 is equal to f. So you can write it as 25 into 10 power 9 hertz. But 10 power 9 hertz is 10 power 9 giga. So it is 25 gigahertz. See, I wrote it as 25 approximately because 2 pi, I took it as 3 into 6 into 2. So 1.5 and 6 on that was like 4x. Which one? 2 pi by lambda. 1 by lambda is wave number. Angular again the word on the you should multiply the number with 2 pi. Write an expression for the electric field. Can you do that? You guys do it, I'm not doing it. Same thing. 60 மட்டும் மாறும். Z கிடையாது, X தான். Electric field's vibration is in Z, propagation is still X only. நான் அதான் சொன்னேன், whatever is here. Oh, E is Z in it. Okay, that is right. So Ez will be equal to E naught is how much? B naught into C naught, correct? B naught into C naught na 60 item. 60 into sine of the same thing again. Whatever is there here, write the same thing. 0.5 into 10 power 3x plus 1.5 into 10 power 11 volt per meter. Generally, we don't write it as Newton per meter, we write it as volt per meter. Is it clear for everyone? Any doubt? Sure. You want to look at the board? Clear. So I've explained about the propagation and I've shown you the equation of how it works, right? Now the question is, what is the source of an electromagnetic wave? Okay. See, since electromagnetic waves are time-varying electric and magnetic fields, try to understand this. They're time-varying electric and magnetic fields which are vibrating mutually perpendicular to each other. Now, the important point that we need to know is who is the source for electric field and who is the source for magnetic field, for which we need to go back to our previous topics. So if at all I have to speak about electric field, who generates electric field? Who will generate electric field? For electric field, do you need a moving charge? If you generally have a charge, it will produce electric field. So what should happen is, if I have a charge which is at rest, suppose I have a charge which is at rest, then what will it generate? It will generate electric field, yes. But the question is it a time-varying electric field? Time-varying electric field? No. It is not a time-varying electric field. Right. So if the charge is at rest, then there is no current generated. If there is no current, there is no magnetic field. Am I clear with this? So what is happening? If I have a charge which is at rest, okay, electric field is generated, but the electric field is not time varying, so it is not going to have it's not going to be an electromagnetic wave. In a similar way, the charge which is at rest will not generate current because the source of a magnetic field is current, charges in motion. So this is not happening. So it is clear from this fact that a charge which is at rest cannot generate EM wave. Am I right? So charge which is at rest cannot generate EM wave at all. Now the question is, if I have this charge which I make to move with a non-zero velocity, but a constant value, then what can happen? So if electric field is going to get generated and magnetic field will also get generated. Yes, they both will get generated. But if you recollect the fact, again, what will happen to the value of electric field? It is not going to be, it is not time variant. In a similar way, B is also not time variant. As a result of which, again, there is no EM wave generated. Is it clear? Now, if I take the same charge and give it a non-zero velocity and a non-zero acceleration also, then yes, electric field will be time varying, and this time varying electric field would generate what? The time varying electric field would generate a time varying magnetic field, as a result of which you can say that there is an EM wave that is generated. Am I clear with this point? Okay. So if you see, what is the source for an EM wave? What would you say? It is basically an accelerated charged particle. So an accelerated charged particle is the one that can generate EM waves. An accelerated charged particle, or you can say an oscillating charged particle. So from this, I hope I'm clear that if somebody asks you what is the source of an electromagnetic wave, you need to simply say that the charged particle that is there needs to be put into acceleration or it needs to oscillate. Just give me a minute. Seeing a document. Okay. So this is all about the source of an electromagnetic wave. And here, what will happen is, since I'm using the word oscillating charged particle, it has a frequency associated with it. So when something oscillates, it has a frequency associated with it. So frequency of oscillating charged particle is equal to frequency of the EM wave that gets generated. So frequency of the oscillating charged particle is equal to the frequency of the EM wave that is getting generated. So what do I mean by this is, when you talk about an electromagnetic wave, there are different kinds of electromagnetic waves specific to the spectrum. You have learned this in your chemistry. Did you learn radio waves, microwaves, infrared waves? Yes. So all these waves have different kinds of frequencies, but they fall under the category of electromagnetic waves only. So if you want a wave of a particular frequency to get generated, then you need to take a particular charged particle and oscillate it with the frequency that is required for us. Okay. That is why I use this statement that frequency of the charged particle is equal to the frequency of the electromagnetic wave. Is that clear? The next one is called as electromagnetic spectrum. Okay. So generally what happened, this is like a history only. So there is a theoretical part where I have not much role to explain. I'll tell you how you are supposed to study, where this part you can do on your own. So generally at the time, there is something called as Maxwell's equation. So Maxwell's equation mainly speaks about a correction that was done to Ampere circuit law. You know what is Ampere circuit law, right? What is it? The line integral of B dot dl will be equal to mu naught times I, where I is the current enclosed by the Amperian law, right? So there was a small correction done for it within a capacitor. Okay, based on this, he gave a concept called as displacement current. So at that point, what happened when Maxwell predicted the existence of electromagnetic waves? So he was a scientist who predicted. So what happened is, there were only few electromagnetic waves that were known. One is the visible light rays, obviously the ones which you can see. Okay, the existence of ultraviolet and infrared rays were barely established. But at the end of 19th century, what happened? When the discovery of atoms took place, you know that in atom itself, there are different kinds of evolution that took place. What do I mean by evolution? Like one scientist proposed plum pudding model, right? Thomson's plum pudding model. Then there was another scientist who disproved, saying that it is not right. There is not this kind of an atom that can exist. So that was done by Rutherford. So what did he do? He did an alpha ray scattering experiment. From that, it was understood that most of the atom was completely empty. Correct? And then came the term called as nucleus. Algorithm, what happened? This theory was proved wrong by another scientist. Good. So what did both say? So the small difference between what Rutherford and Bohr told is, Rutherford told that electrons revolve in circular orbits. But Bohr told that electrons, yes, they do revolve in circular orbits, but they cannot revolve in a random circular orbit. Rather, the circular orbit should have the energy quantized. So he came up with the concept of quantization, and those orbits he called it as stationary orbits. I'll tell you why I'm talking about all these things. Okay. Then came the concept where excitation of electrons and de-excitation of electrons could take place. If you have an electron in a particular orbit, and if you want that electron to get excited to a particular state, what are you supposed to do? You need to supply energy to it. So when you supply energy to it, whichever is required, which is the energy difference between the orbits, then the electron from one stationary orbit will jump into the other stationary orbit. It cannot lie in between. That is for sure. Right? This is what we call as absorption mechanism. Energy absorbed and the electron jumps from lower to higher. Suppose the reverse thing happens. Electron jumps from higher to lower. Energy is released. And the question is, how is that energy released? So energy is released, okay. That energy gets released in what form? That is why I wanted to connect it. So the energy gets released in the form of electromagnetic waves. So in that electromagnetic waves only, depending on the transition orbits, Means if an electron is able to jump from a higher orbit to the first orbit, then there was a series which was discovered. This happened only with hydrogen atom. Okay? It's not with all other atoms. It happened only with hydrogen atom. So hydrogen atom, when an electron jumps from an excited state to the first orbit, then there was a series called Lyman series that came into picture. And that Lyman series belonged to the ultraviolet region of electromagnetic spectrum. That is why the statement is given 19th century these things got clear. Yeah, the 19th century what is important because 1920 is the time 1920 is 20th century actually. It is somewhere around that time this kind of existence came. So that is ultraviolet rays. Similarly, when an electron jumps from higher orbit to third, fourth, or fifth orbits, then it falls under Paschen bracket or Fund series, P-Fund series, which were confined to infrared region. In a similar way, when an electron jumps from higher orbit to second orbit, they belong to Balmer series, which belong to the visible region. So all the company, what they did was they started, since you have these many electromagnetic waves existing in nature, it was difficult for us to read everything under the same umbrella. So what we can do is we'll try to break them into different branches, and they wanted to come up with the concept of something called as spectrum. So that's why we call this as an electromagnetic spectrum. Why is it done? Mainly to make our understanding simple. Okay, so that you can give different names to the same to the electromagnetic wave, different kinds of electromagnetic waves that were existing. So this is all about the electromagnetic spectrum. But I will read it out. By the end of 19th century, X-rays, gamma rays, you know that nucleus is there. So there are two things we need to discuss. Within an atom, if an electron jumps from a higher orbit to a lower orbit, energy is released in the form of electromagnet. That is either ultraviolet ray or visible ray or infrared ray. But if there is a necessity where you need to have gamma rays, then there is something called as nuclear disintegration that needs to take place. I'm talking about two things here. When an electron is not in its original orbit, when it is in an excited state, you say the atom is excited. Whereas there is a possibility where the nucleons present in the nucleus will be under imbalanced condition. When that kind of a scenario happens, the nucleus itself will get disintegrated. So try to understand. Atom electron jumping from higher to lower orbit is only excitation and de-excitation process. Whereas the nucleus itself is getting disintegrated, and it's called as a nuclear reaction. So generally, when these kind of nuclear reactions take place, there are different kinds of rays that are emitted. Basically, among which one of the rays is called as gamma rays. The other two are called as alpha particle and beta particle. Difference, right? So that is the meaning of X-rays, gamma rays, radio waves, and microwaves, and ultraviolet and infrared waves are generated. So the classification of EM waves according to the frequency. So you start categorizing them according to the bracket of frequency range to which they belong. They do not have a fixed frequency. They have a range of frequencies. If it falls between this to this range, you can call it as some electromagnetic wave, or else you will call it as something else. Okay. So Adhe Mari Bhattana, there is not exactly a sharp division where you can say that this ray is different from other. There might be a cusp also, cusp in the sense which will overlap. So there is no sharp division between one kind of wave and the next. The classification is based roughly on how the waves are produced or how they are detected. So these are all experimental aspects, which I cannot show it to you. It will be dangerous to handle. So when you look at the spectrum, you have two sides. On the left side, you have frequency range. On the right side, you have wavelength range. So if frequency is given to you, how will you find the wavelength? So wavelength is distance. Simple. Distance is equal to speed into time. So distance is wavelength is equal to speed into time can be written as 1 by f. So f is equal to v by lambda, or v is equal, lambda is equal to v by f. Am I clear? So if you know the frequency, you will be able to derive the other side and the vice versa. Breathe up. Okay. So when you come from the bottom, you have something called as long radio waves. Okay. Basically, if you're able to see, there is an overlap that is taking place here. Similarly, there is an overlap that is taking place here. So similarly, here also you have some overlap that is taking place. That is why they told there is no sharp distinction where you can say this belongs only to this. So depending on their use and the way they are produced and how they are detected, they are classified into different categories. If you take the waves of lesser frequency, they are basically the radio waves. That is why if you see the radio waves which we are using are for communication purposes. You're using your mobile phone or Wi-Fi or whatever it is. Everything runs on the concept of radio waves. So radio waves have a certain frequency that are associated with. So where does the frequency start from? According to this electromagnetic spectrum, I am able to observe that they belong somewhere between 10 to 10 power 12 hertz. So 10 hertz to 10 power 12 hertz, where their frequency is going to exist. That is why I think I have already told this when I discussed about the newness of it. When you talk about FM another frequency, it's called frequency modulation. So it is not frequency manipulation or something, it is frequency modulation. Modulation in terms of communication language means you take a message signal and mix it with a carrier signal for sending it for longer distance. Carrier signal and other high frequency signals. Message signal is my voice. So these two will be mixed together and they will be transmitted to longer distance. When they are mixed, if there is a change taking place with respect to the frequency of the carrier wave, means with the help of the message signal, if you are able to modulate the frequency of the carrier wave, you call that kind of a process as frequency modulation. அதே மாதிரி இங்க ஒன்னு தெரியுது AM radio தெரியுது. What is AM? AM is modulation. A stands for amplitude. So what does a wave have basically? Amplitude, frequency and phase. So if the frequency is changing, we call it as FM. AM amplitude modulation. If you are able to vary the amplitude of the carrier wave, we call it as amplitude modulation. So radio waves is again classified as long radio waves, AM waves, television and FM radio. Other television and FM radio is what is falling between 10 power 7 to 10 power 9. If you see every channel that is present, the FM that you are able to hear, you see their frequency range is somewhere between 88 megahertz to 108 megahertz. You cannot find a channel. You cannot find a channel. If at all something you're using, if you're using any other frequency for communication, it is illegal. The terrorists come with them. So when you have license, you need to use it only between 88 to 108 megahertz. Is very clear? So above radio waves, you have something called as microwaves. So where are microwaves used? You already know. We have it at the microwave ovens. So there we can use microwaves. Similarly, above that you have infrared waves. Where are infrared waves used? These are all infrared. Similarly, if you see, I'm able to, you'll be able to see something on my screens. See, suppose I'm doing something, but observe my screen, you're able to see something. I'm going to go for airdrop. So from my phone, from my phone, I'm transferring something to the iPad, and if I click on this, it's going to ask me. So how did this transfer even happen? So this happened based on the airdrop option. Airdrop is the feature. But the airdrop's backend feature is it works on the principle of infrared waves. I'm not sure if you have heard of all these things. There is something called end transfer, where you need to bring two phones in contact with each other and transfer. When the mobile phones came into initial time, from one device to another, you need to bring them in contact because infrared is a short range frequency. Another remote and all, you cannot sit in the park and you cannot operate it. So it has to happen within a room. So you're able to understand. The next is ultraviolet. Okay, above that you have X-rays, above which you have something called as gamma rays. So each of these waves that are there in the electromagnetic spectrum are generated in a particular way. So this part I'm leaving it to you. I'll tell you how to read. You go through it. There is nothing for me to teach. If a radio waves first, when you go from bottom to top, radio waves, microwaves, infrared, ultraviolet, then you have X-rays and gamma rays. Is an order. So when you talk about radio waves is an electromagnetic wave. So for me to generate an electromagnetic wave, what is the first thing I need to do? I need to take a charged particle, put it into oscillation. How much should I oscillate? I oscillate it to the particular frequency which I need. If I want to generate radio waves, then everything starts like this. Radio waves are produced by the accelerated motion of charges in conducting wires. Okay, why do we use them? Radio waves, why do we use them? Name is suggesting radio and television communication system. Okay, and how are they generated? They are generally in the frequency range of 500 kilohertz to about 1000 megahertz. So the AM amplitude modulated band is somewhere between 530 hertz to 1170 kilohertz. Higher frequencies up to 54 megahertz are used for short wave bands. Okay, DV waves range between 54 megahertz to 890. FM radio band extends between 88 megahertz to 108, other licensed band. Okay, so cellular phones use radio waves to transmit voice communication in the ultra high frequency band. And actually, the important applications of all these you will actually learn it in communication chapter, but that is very good. So communication, you have something called as a ground wave, then you have something called as a space wave. So you know how, so basically waves are transmitted through the process of reflection. Send it to one point, hit it, and reflect it back to some other point. That's the logic they use. So if you send it across the ground, across the level of ground, you call it as ground waves. For example, if you would have seen these transmitters outside, the telecommunication channel will have a transmitter, right? If the transmitter is sending the signal from one transmitter to another along the ground level, you call it as a ground wave. You is sending to some satellite, and from the satellite it is getting reflected, you call it as a space wave. So in the Mari area, depending on the application they use it. It is all engineering level. What I'm talking about is okay. Similarly, when you talk about microwaves, they also have a certain frequency range, which are in terms of few gigahertz. Okay, how are they generated? By special vacuum tubes called klystrons or magnetrons and gun diodes. So how the question in example comes? What are the electromagnetic waves which are generated using special vacuum tubes? Or they will ask you, what is the frequency range of the electromagnetic wave which is generated using special vacuum tubes? So first thing is you should know that special vacuum tubes will generate microwaves. Then you should know what is the frequency range of microwaves. Or what is the application? What is one of the applications of electromagnetic wave which is generated using special vacuum tubes? So first special vacuum tubes now microwaves. So then you should know what is the application of microwaves. So this is how they ask. So in the whatever paragraph that is given here, break it into chunks and prepare your notes. That's it. Now the prepare when you study, that's more than sufficient. You have to remember it. I've told you the outline of how they are generated. Okay. So don't expect me to tell the numbers. You should be able to remember it. Second, that part I'm leaving to you. With this, 90% of the chapter is over. I need to check if displacement current is there or not. Is it there? Not sure. Because last year they deleted. If it is not there, the chapter is over. I need to explain two derivations alone related to energy that I do it in next class. I got the file. the basic idea of displacement current is that I'll explain in the next class. Very sure. So it's a very, very, very small chapter. So finish it. Ray optics will take time. Next one. Sorry. So those who are online, I hope you are able to understand.
Yes, sir.
Okay. So that's it. So that's all for today. I'll see you all on Monday. We'll wind up.
Thank you, sir. Bye.
Bye.